So, I will give you some homeworks which you can try, but you should try some of these homeworks for sure. For example, there was one involved in the kernel of homomorphisms. Okay. That is a central result in not merely group theory, but it comes all over the place. Okay. That idea. Okay. It's very simple. So, you should try that. But now, I will give you 3 more homeworks. Seven, 10, 12. Okay. Try them. Okay. They are not difficult, but they involve you in trying to think through the concepts. So, in that way, it is definitely useful. Okay. This book is my book. Okay. And you can download it from the internet and you can give me the money. Okay? Yeah. They will arrest me. The book publisher will arrest me. But yeah. Okay. So let me start. What I am doing now is enter into the central set of topics of group theory from the physicist's point of view, namely representations of groups. Okay. So last time, I think this chalk is writing okay. Okay. So group G. Okay. So we define this a representation, okay. Let me call it pi, okay, of a group G is, there are 2 aspects. By the way, some of you, I get the suggestion that you are interested in formal things. Okay. Then I would also ask you to come for the Monday talks, okay, where I am doing quantum mechanics from a more foundational point of view, okay, like things like fiber bundles and so on, which again are not difficult, but involve new concepts, okay, which my impression is that it is not readily available to students unless you are in math. Okay. But they are very central. I mean, if you do quantum field theory or condensed matter physics, it is if you want to do quantum field theory or condensed matter physics in and you are interested in conceptual framework, then it is unavoidable. You have to know it. Or if you do defects in crystals and so on. Okay. So it may be worth your while also to drop in, although you have missed 2 classes, but that can be made up. So here, representation of a pi of a group G is a homomorphism. So there are 2 things here. It's not just a map, okay, from G to linear operators on a vector space. So this is normally written as NV. This means endomorphisms of a vector space. Okay. And we always consider complex vector spaces. Okay. Real vector spaces is a bad story. Okay. You cannot diagonalize operators, so you get into all kinds of troubles. Okay. If you try to take a real vector space and you take even a 2 by 2 real symmetric matrix, you may not be able to diagonalize it. Okay. For example, this matrix. So this is, we take this matrix, cos theta psi theta minus sin theta cos theta. Okay. This is a symmetric. This is a real what is it? Orthogonal matrix, real orthogonal. If you try diagonalizing it, In a real vector space, you can't do it. It has complex eigenvalues, you cannot do it. So, the entire thing about self-adjoint operators having complete set of eigenvectors and real eigenvalues, whole thing fails, because you cannot diagonalize operators. Okay. So, real vector space is a bad story. Okay. For us physicists, it is achut, we don't touch it. Okay. Okay. So, we don't want it. So, I will say complex. So, what I have got here is a map pi of G into pi G, where pi G is a linear operator, okay, which is normally written as end of endomorphisms of V. This is the same word we came when you have a mapping of a group G into a group G. It means it preserves the structure, that is all it means, okay, but may not be one to one. Okay. So, what you have got, this is a linear operator. So, this means pi of G1, pi of G2 is pi of G1, G2. Okay. It is a homomorphism. Okay. So, that is this equation here, and the multiplication here is multiplication of linear operators or matrices. Okay. Very often you will find more and more frequently this language used. V, people say, is a G module. This usage is particularly common in mathematics, but it means this that it is a representation space for G. Huh? Endomorphism means simply a linear operator on a vector space. Endomorphism for a group is a mapping of a G to a group, which is a homomorphism. G to G, which is a homomorphism. Okay. Acting on a vector space, it is just a linear operator. Okay. It preserves the structure. It's a linear operator, so it preserves the addition properties of the vector space. Right? X plus y, Lx plus Ly is L of x plus y. Yes? Yes? So, it preserves the structure of the underlying space. So, you call it endo. Okay. Morphism means shapes, morphos, yeah. Okay. You are not here in the last few classes, so maybe you should look, but we can talk. If you have trouble, you can come to my office in 325. Okay. So, last time I gave you examples, okay. I gave you several examples. You can refer. I will go on now to last class. I gave example for translations and I think rotations, self representation and so on, but most importantly I gave you the right, especially the left and right regular representation. You remember how it was defined? Okay. You remember in these representations what you do is, so here V are functions F which map the group G to complex numbers, okay, and the two representations, okay, let us say. So, this is a function, okay, and the left representation is defined by pi L, let us say, of H sends F to pi L of H of F, okay, where pi L of H F at the point G is, you remember what it is? We defined it last time. Okay. This is a transform function f of H inverse f of H inverse G. Right. This inverse is important, as I showed you, to preserve this equation here. Otherwise, you will get the things in the wrong order. Okay. Likewise, we define right. It also acts in the same space. Pi r of h f at G is f of gh. It acts on the other side. Okay. And they commute. These two representations commute. I see people from quantum information and so on. There is some theorem called Stein-Spring theorem, okay, which is used in connection with proving certain theorems on maps. Okay. That is a simple generalization of these ideas. Okay. If you look, it is really this. Okay. And if you combine this idea and something due to Gelfand and Neumark, you get that thing. Okay. So, just a side remark, but you do not have to know what it is. Huh? Anyway, let me go on. Okay. So, this is where we stopped last time. Okay. And now we want to set up, understand how to build up representations. What happens, why representations are important? Because in quantum theory, especially in quantum theory, every symmetry operation is given by some linear operator. Okay. So, a symmetry of rotation will be a linear operator like this, where G is a rotation, or SU2 or whatever it is, or it could be a Lorentz transformation. So, this is some linear operator acting on your wave functions, but this mapping from the transformations like Lorentz transformations into linear operators has to preserve this equation. It has to be a homomorphism in order that if you do two rotations in space and they represent it on my wave functions, they should compose in the same way. Okay. So, you necessarily get representations of symmetry groups on your quantum wave functions. Okay. So, we have to understand representation theory very well to be able to do any meaningful quantum theory. Okay. Of course, you can mess around, but you have, if you are interested in some conceptual framework, then this is very important. Okay. If you want to appropriate the basics of the subject into yourselves, this is needed. Okay. So, let me see what is, so we have to know how to build up representations, and for that we have some basic ideas. One is reducibility of representations. Again, I emphasize, please feel free to ask me questions. There is no hurry, I can stop anytime. Okay. So, let me say this one. Suppose T is a linear operator on V. Okay. Then suppose V0 is a subspace. Okay. Of course, I will say it is not the trivial one or V itself. Invariant, well, I will tell you what I mean by invariant under the action of T. Of T. So, application of a linear operator. So, that means x in V0 implies Tx is in V0. Okay. That is, if you take a vector in V0 and apply this operator, you get back a vector in V0. So, that is, we write this normally, the T acting on V0 is contained in V0. Okay. As a set, it maps into itself. Then we say that V0 is an invariant subspace under T. Okay. We think of T as an action on this, very much like some Hollywood movie, Rajinikanth doing an action is like that. See, it is pushing, doing something. Okay, now we want to understand this T little better. So let me see what might be the shape of the matrix of T. Okay, so I choose a basis. Okay, for V such that, say, the first k of them span V0. Okay, rest I don't care. Then the matrix say M of T looks like, can you tell me? It's not exactly block, you are almost right. Certainly there will be a 0 here because it does not take V0 outside V0, so it is a 0 there, right. But I did not say that it does not do pull things from outside into the interior, so there will be something here and something here and something here. It will be upper triangular, right. So if I take a vector where there are 0 0 here and anything here, under this transformation it will again go into a vector of the same sort. Yes, because this will not pull here, pull the top to the down, so it will be upper triangular. Okay. So this is the shape of a matrix which leaves a subspace invariant. I did not say anything about an orthogonal a complementary subspace. There is a complementary subspace here. I did not say how it behaves under this T. Maybe it pulls it back, I do not know. Okay. Now, it can be block diagonal, in which case this is 0. Okay. So block diagonal is a special case. Hmm? So there will be some, anything you like, any matrix of this kind. So if I take any M1, M2, M3, 0, okay, where M1 is a size adjusted to this, is a square matrix of this size, M2, M3 is a square matrix compared to this one, right, and this is a rectangular matrix, will do the job. Yes, because it will, acting on this, it will not bring the zeros back, it will not bring stuff here into this. That is all I need, right. If I take vectors in V0, I should stay in V0. Yes. So a representation pi of G on V is reducible this is an idea if there exists V0 just like not equal to 0 or V, okay, invariant under all pi G. Okay. So if it is a reducible representation, all the matrices look like this. So in a basis, okay, adapted basis, So, I write A1 E1 up to Ek plus 1 say up to some Ek plus n, okay, where this is spanning P0. In this adapted basis, okay, the matrix of pi g, okay. So, if I write pi g on EI, let me write the matrix of pi g explicitly out. It, by definition, this is Ej times some the matrix of pi like this, J is summed. This is the definition of D in linear analysis. So, it is the matrix of pi in this basis dg. Right. So, dg is going to look like some d1 of g, and there is a diagonal here d2 of g, some alpha of g and 0. By the same argument, right. Here d1 of g is k cross k, some k cross k matrix, okay. Alpha of g will be, I think, k cross n plus n, k cross k what n is a triangular, no, let us see the number of this is k cross, this is k, this is k. So, I have to full n. So, it will have n columns and k rows, then d2 of g will be n cross n. Okay. It will be blocking like this. Now, let us see what happens if I apply d1 of g. This cannot be completely free, because if I take d of g1, d of g2, it is d of g1 g2. So, that puts some conditions on this d1 and d2. Okay. So, let us see what it is. You get d1 of g1, alpha of g1, 0, d2 of g1, then I multiply this by d1 of g2, alpha of g2, 0, then here you get d2 of g2, let me work it out. This is d1 g1, d1 g2, yes, because alpha will go and hit a 0. Here it will be d2 of g1, d2 of g2, here I will get something which is very unfamiliar to most of us, because it will be alpha of g1, right, d2 of g2 plus you will get how did you go? I am alpha of g1 d1 g2 plus d1 g1, right, alpha of g2, and this is 0. Okay. Now, this means immediately this is equal to d of g1 g2, right. So, it is d of g1 g2, d1 of g1 g2, alpha of g1 g2, 0, d2 of g1 g2. This implies immediately that di, these matrices for each I themselves give us representations of G. Okay. But with regard to alpha, it is rather strange. We are getting some equation which says alpha G1 G2 is, as written there, it is alpha G1 D2 or G2 D2 or G2 plus D1 or G1 alpha G2. This equation has actually great importance, but I have no time to this this equation, properties of alpha, okay, tell us if there exists a basis, there exists a V2 such that, okay, the full vector space is V1 plus V2. You may not have understood direct sum, I will come to it in a minute. Okay. So, I have not told you what the complementary subspace is, okay, such that, okay, D or G, the new G, new D or G, okay, becomes block diagonal. That is with alpha 0. That is this study of this equation tells it is what people call as some cohomology condition. This is looking very simple, but there is some algebraic structure underlying it, okay? And it is something related to what people call as group cohomology, and you can tell by studying some properties of group cohomology whether there exists this V2 so that you can reduce this to 0. Okay. So, anyway, never mind. What I wanted to make is this major point, okay, that the block diagonal property is coming out. Okay. So, let us look at examples. First example is something we studied, translations on a line. Okay. So, it is the group law is addition. Okay. So, translations, let me call it TA. So, TA acts on a real line x as x plus a. We looked at it last time. Okay. Then TA TB is T of a plus b from here. Okay. We found a matrix representation of this one last time. Okay. Its two-dimensional representation is, let me call it dA, which is 1A01, is upper triangular. We saw this thing earlier, right? I will prove to you little bit later that there is no choice of basis where this entry can be made 0. We will see that it is impossible to this is acting on a 2-dimensional space, and there is an invariant subspace, namely the vectors of the form x0. Okay. So I can ask, can I find something, some complementary subspace in such a way that this thing becomes, the off diagonal entry becomes 0, and we shall see that this is not possible. I will prove it to you. Huh?
Seems like see the translations on line, that's a one-dimensional system, and the representation is two-dimensional. So is this related to what he's not here today, but he asked about the 5-dimensional representation?
It is related to that, because what you do to get this is you homogenize it. Think of this x as a homogeneous coordinate, that is, you write x is x1 over x2. Okay. Then rewrite this equation as TA of x1 over x2, right, as x1 over x2 plus a, then you multiply. So, you get TA of x1, right, is x1 plus a x2, right. Then you simply define TA of x2 is x2. Okay. So, you think of this x as what they call homogeneous coordinates, that is, as ratios. Homogeneous means if I scale either, this does not change, okay. Then linearize it, then you will get this representation. Okay. Yes, you take a 4-dimensional thing and then again introduce this 5-dimensional coordinates by introducing ratios. Introduce an extra coordinate and think of your 4-dimensional coordinate as a ratio, then clear the ratio, then you will get the answer.
So, but this extra coordinate doesn't have any actual
physical? No, but it is it's convenient because this equation is homogeneous in the variables, right. So, if you think of these equations as equations defining a homogeneous, that is a projective surface in 5 dimensions, or in this case 2 dimensions, you will get that one. Okay. So, people doing algebraic geometry all the time, they do it. They write some equations in complex variables for a surface. They will write some equation like z1 cube plus z1 z2 squared plus etc. equal to 0. Okay. Where z1 and z2 are all complex variables in some complex space, okay. C, in this case C2 or something. Okay. Then you say, read this equation as a homogeneous equation. That is, what you want is not this, but this modulo a complex scaling. Okay. So, if I scale this, they are all of the same degree and you have 0 here. So, clearly if I have one solution, z1 times a complex number is also a solution. So, you think of it as a scaled, the surface you want is not this surface, but the projection of it to a lower dimension by the scaling. Then you get all these algebraic varieties people talk about.
So it's like you nest it in a higher dimensional space.
It's convenient because if you try eliminating them, you will find that you cannot eliminate them all the time. Okay. I mean, you have to choose. For example, here if I try eliminating by homogeneity, I divided by x2, but here there are some places where x2 is 0. So, I have to then change my rule suddenly and start eliminating x1. Okay. Then you have to give rules on going from one elimination to another elimination. Okay. So, you do not want to do that. Okay. So, normally projective equations, the complex algebraic varieties are written normally like this. Compact, yeah. It is just a trick. Okay. Because extra coordinate means more degree of freedom, you do not have to start worrying about what I am dividing out by and so on. Okay. Then you can deal with this more easily. Now, if I take the translation group on R2. So, I have two variables. Okay. So, the elements of this group will be now T of A1 A2. This is a two-dimensional representation. Say so, 2D rep. Okay. It will be D of A1 A2. I will write this as 1 A1 plus I A2 0 1. Okay. This is good because here things add, and since I have put a complex number, you can separate the real and the imaginary parts. It has a 4-dimensional representation, which is also canonical. So, let us write this out. The 4-dimensional representation is the following. Okay. It is let us say D4 of A1 A2 it is a Kronecker product 1 A1 0 1 1 A2 0 1. Have you come across this in your studies? It is called the Kronecker product. Okay. Have you come across it? No. It is a 4 cross 4 matrix. So, it has a very simple geometrical meaning. Physics is, this activity is very important. So, this is first I put 1 here, 1 A2 0 1. Okay. Then I write A1 times 1 A2 0 1. Here it is 0. Then I write here 1 1. 1 A1, this whole matrix I am making a mistake. So, here I write 1 A2 0 1. Okay. So, this is called the Kronecker product. So, this product is Kronecker product. This is a very simple meaning. Quantum mechanics we do it all the time when I consider two particle wave functions. Okay. So, this is a 4 by 4 matrix. So, what I have done is, okay, let me say just so that people follow, remark. If L1 is a linear operator on V, some vector space V1, L2 on V2, then this thing L1 tensor L2 acts on V1 tensor V2. I will give you the formal statement of what this is for those of you who are curious now. Okay. By L1 tensor L2 acting on X tensor Y is what? L1X, right? Tensor L2Y. Okay. The matrix, if let us say Mi are matrices of Li in basis, okay. So, let us say E I for V1 say Fj for V2 choose anything, okay. Then M1 tensor into the Kronecker product of the matrices is matrix of L1 tensor L2 in the tensor product basis, in basis EI tensor Fj. Okay. So, if you are this activity of Kronecker is writing it out in a basis. Now, just for those who are mathematically inclined, so I should say this is remark 1. So, you may ask what do I mean by this tensoring, okay. 2 is x tensor y, or x, very often people write x tensor c on y. Have you seen this? Means, okay, the pair xy, but you say it is equivalent to, okay, with identification what lambda x y is x lambda y, all lambda complex numbers. Okay. So, this object here, in quantum mechanics, what do you do? In quantum mechanics, this is a wave function, there is a wave function, and you put them together. So, if I multiply this by a complex number, it is equivalent to multiplying this by the same complex number. Okay. So, that is what we mean by this tensor product, and this also means, because it is acting on such a space, here also if I multiply this by a complex number, it is equivalent to this. Just a remark. This activity is not so important if you are only dealing with complex equivalences, but it happens also in physics. It happens that many times these complex numbers are replaced by other things. Okay. It could be replaced by some cyclic group Zn, very often this happens. So, you will see if you do say non-commutative space times, you see very often here they are very careful to write, and you will find this Zn appearing. What does it mean? Well, you replace the lambda by any root of unity, okay. Then the structure of the space changes completely. Okay. You can quotient this Cartesian product by anything you like, provided it is compatible with what you want to do, but you do not want to do random things. Okay. So, quantum mechanics we are quotienting out by complex equivalences, but in some topological considerations you want to consider other quotientings, okay. Very naturally from the physics point of view. For example, if you have defects with a fractional statistics, you may want to quotient by some discrete groups, and this happens. So, this is just a remark. Okay. Now, likewise, okay, there is another operation we need to consider when I consider representation theory from a physics point of view. Okay. So, example, given two representations di of a group G, we can form the direct sum D is D1 plus D2 is a representation d of g is along the d1 of g 0 0 d2 of g. As a matrix, if I think of everything as a matrix, you just put them along the block, along the diagonal. Okay. Which way you put is doesn't matter, because I defined for you equivalent representation. I think I gave you the definition of equivalent representations, right? If one can be transformed to the other, okay, by a matrix S. Okay. So if you put the other way around, it won't be anything. Okay. So let me. I don't know whether I did it. Okay. Record two representations okay, say pi 1 and pi 2 on vector spaces v1 and v2 are equivalent when? If there exists an invertible linear operator okay, from S, which takes you from V1 to V2, could be two different vector spaces such that if I acted pi 1 of G first, so it is acting on V1, apply S is the same as S acting on this way. Okay. Or you can write pi 2 S or pi 2 of G is S pi 1 G S inverse. Could be different vector spaces. Okay. If in the same vector space, it is a change of basis. But very often we will be given these things in completely different avatars. One will look on some complex vector space, the other will act on some functions. For example, you may have come across rotations, okay. Say rotations act on R3, right? Rotations, 3W. But they also act on spherical harmonics, y1m. These are functions, three functions, m equal to 1, 0, minus 1. Okay. These are the spherical harmonics of order 1, angular momentum 1. These two representations are equivalent, but they are these are functions and those are some real some three-dimensional vector space. Okay. So I have to make a, how do I tell that they are the same? So there is a mapping from here to here which has these properties. So if they are the same vector space, there is no problem. Okay. Many times that is not the case. Yeah.
Dimension of V1 and V2 is the total vector dimension, right?
Sorry?
Total vector space. Total vector space, there are V1 plus V2 number of vectors in it.
I will define for you now what is meant by V1 plus V2. V1, V2, if you write components, you just write them in a big column.
Yes, but all groups shouldn't all group when group act on a vector space, all others vectors can be reached.
No, not necessarily. No. There will be, if there are invariant subspaces, like I told you, that is not the case.
Invariant means
V0. I gave you the example of V0. From V0 you cannot reach vectors outside. Right?
V0 has less vector than the
total vector space. So I cannot go out. Yeah. So I will finish today by giving you a formal definition. Oh, yeah. or what is meant by direct sum. You may know it by components. It's good to know it more better way, because next I will be looking at full reducibility, irreducibility and Schur's lemma. These are absolutely, Schur's lemma is absolutely the crucial result, okay, for much of representation theory from the point of view of physics, okay, both for finite groups and for rotation group, things like rotation group, Lorentz group, everywhere this Schur's lemma comes, okay, and it is very simple to understand, but it is better to think about it more abstractly. So, how will I define? So, for today the last item is, okay, a very good reference is Halmos. For finite dimensional vector spaces, okay, if you know this book, there is a book by Halmos called Finite Dimensional Vector Spaces. Yeah? It's a really fantastic book. Now, if V and W are vector spaces, okay, what we do is the elements of V plus W are what? Vector here and a vector there, okay. So vector x from V, x is in V, y is in W. Okay. We have to tell the sum, okay, the operation summing, okay, by definition, okay, where also you have to tell x y plus x prime y prime. We add component wise, so it is x plus x prime, y plus y prime. Okay. The 0 is the pair of things. Now, V plus W contains let us say V, okay. So, that will be vectors of the form x0. When I say V, that is not a V, it is up to isomorphism, that is V, if you think of V as an additive group, there is an isomorphism from the starting V here. So, you take x and map it to x0, and likewise it contains W, which will be 0 y. So, when I say V and I made this one again after these identifications, because I have increased the dimension and a subspace here looks like what we started from. Now, if say L1, L2 are linear operators on V and W, their direct sum, okay, L1 plus L2, okay, is a linear operator. On V plus W. How will I define it? The most natural way, defined by right L1 plus L2 x plus y, well, on x y you simply act with L1, L1x, L2y. Yes. If I now choose a basis, okay, if EI Fj are bases for these two subspaces, namely VW, then it is pretty obvious the matrix of L1 plus L2 block diagonalizes, right, gets blocked as we did earlier. So, it will be here 0 0 here. Okay. I should say in basis EIFJ. So, I take the adapted basis, take the first set, in the direct sum, in the first entry I choose the original basis, second entry I choose again the original basis, they provide the basis for the direct sum. Find the matrix of this direct sum operator, it block diagonalizes. Okay. It's almost is obvious. Okay. So, the direct sum of two irreducibles, the direct sum of two representations I constructed was this activity. Okay. Okay. The direct sum, okay, d1 plus d2, I think that is what I called, was constructed this way. The advantage of this way of thinking is that it is basis independent. Okay. If I now until here, if you give me V and W, this is defined. Okay. Now you can choose a basis which is not looking like this. Okay. You can make a linear transformation on this V crow. We have seen. Okay. Then I stop with that. So, given representations pi I, we can find new ones, okay, say pi 1 tensor pi 2 tensor right, etc., or pi 1 plus pi 2 plus pi 3 plus etc. I can construct pi 1 may be equal to pi 2. In fact, here if I take pi 1 and pi 2 as the same, when you take this tensor product you will get new ones, okay, really new ones which you did not know about, but direct summing most puts things on a diagonal, is simpler. Okay. By the way, you can check this cross here and plus are associative. You understand what I mean? I have proved, I discussed two of them, but how do I know that if I do this first and then I put that, if I, that is pi 1 cross pi 2 cross pi 3 is equal to pi 1 cross pi 2 cross pi 3. It's very easy to prove, same for plus. So you don't have to put brackets. That's a side remark. So this is a way of so let me finish up by saying this kind of activity corresponds to multi-particle representations. That is, if I have a one electron transformed by rotations and I have a proton transformed by rotations, how do they transform? If I have an electron and a proton, you get this one. Okay. This one is not multi-particle, it is a where does it come? If you have multiple, it comes, for example, if you have multi-component wave functions. For I don't know right away of a direct sum, in terms of composition of particles, you don't get this, you get this. Here I cannot right away think of a simple example in physics. Okay. First one, yes, okay. That is what we normally do. Okay. If you do scattering theory, you get this, the incident state will be a two particle state. So it will be composed of, say, proton and a proton. So the wave functions are coming from a tensor product space. Okay. In that case also you get a tensor product, that is orbital angular momentum times spin is a tensor product. Okay. Direct sum, yes, but you see, if I write spin, say spin half, so you have two states, m, and I have, suppose the particle has also angular momentum, you will write j3, right? Yes, this is a tensor product. Direct sum comes when I try to take this apart into some smaller blocks, okay, which I will describe to you next time. It is called the Klebsch-Gordon problem, basic to angular momentum theory, but I don't know of example in terms of composition of particles right away. There must be, but I am not thinking immediately. So the two books which I like very much is, one is this Halmos on finite dimensional representations, then Werner. This is on group representations. It is an old book, but really excellent. For example, the first few chapters he discusses these generalities very nicely, and then later he discusses finite groups with considerable exhaustion. I mean, representation, I will do it. I will do, at least give you the information, okay, of permutation group and so on. But the theory of finite group representations, like permutation group, is actually very complicated. Okay. It involves some very subtle ideas from algebras, okay, and he patiently goes on telling everything, every step. They are not complicated, but these steps go on adding up. It's not that you are doing very hard analysis and bounds and so on. It is not like that. But little operations, but they, at the very end you don't know where you are. Okay, and he does it very precisely, very clearly. And I will, to some extent, cover those things here. Okay, I don't want to make the course a very baroque one, so I will summarize the results. Okay, mostly. For the permutation group, I will give you some details on what to do. Okay, then we will go into continuous Lie groups. Okay. J is here is this. I am assuming you know some quantum mechanics. So J is angular momentum.
This is same as that cross.
J was an example of a particle with angular momentum J, and third component of angular momentum J3. Okay.
J3 and half m. That is the same as the tensor product. He's saying that it's a tensor product state.
It's a vector space. Is V cross W. It's not it's not a D1. It's not pi 1 cross pi 2, but it is V cross W. The vector space on which the group is acting. J, that is a vector space.
Basis space.
Basis for the vector space, exactly.
So that V cross.
That is the two things. One is you are tensoring vector spaces, but the tensoring or direct summing vector spaces, then correspondingly you have tensoring linear operators or representations, or direct producting linear operators in or representations. Okay. So there are two things here. Okay. One induces the other.
The special function like that.
Huh?
That x minus I y like that.
Yeah.
Other will diagonalize that.
I don't understand.
X minus y that y.
Wow, spherical harmonics. Yes. What about them? That is a vector space. It's not a representation. It is a vector space, and you can apply rotations on that spherical harmonics, and they will transform. Okay. That is why they are used when you do hydrogen atom. If you do hydrogen atom eigenfunctions, you have to make separate coordinates. So you use spherical harmonics. It is those things that come here. Okay.